Okay, Bismillahirrahmanirrahim. So let's solve some problems, a recitation problem for chapter 10. So as you know, we finished chapter 10. Now we will solve recitation problems. So the first problem is this example number 12, which is in the slides. So what do we have? We have a racket-like object, and it's made of a thin rod, okay, of mass m, but also a thin hoop of mass m. Okay. So the first part here is a hoop, a thin hoop of mass m of radius r, as you can see, attached to a rod of length L, which is 2r and of mass m. Now here I put the rotational axis here, as you can see it. The rotational axis is right here. And the question is, what is the moment of inertia of this whole object, of this whole system, with respect to the rotational axis that I just plotted here. So in terms of m and r, find the rotational inertia about this axis of rotation. Okay, let's do it. So here my system is made of hoop plus rod. So the moment of inertia around this axis of rotation here, as you can see it in red, is equal to the moment of inertia of the hoop with respect to this axis of rotation, plus moment of inertia of the rod with respect of this axis of rotation. So what is the moment of inertia of the hoop with respect to this axis of rotation? That's not in your formula sheet, but if you need it, I will give it to you. It's half mr squared. Okay. I have my hoop. It has a mass m and a radius r. The axis of rotation is passing like this. For one diameter, the moment of inertia is half mr squared. If I have the same hoop, okay, and then the axis of rotation is pointing towards you here, okay, and coming out of the plane through the center of mass, the moment of inertia is mr squared. And this is in your formula sheet. But this one is not in your formula sheet. Okay, but let me show it to you quickly. You can see it here. Okay. So here I have a hoop. The moment of the axis of rotation is passing through the center of mass. What is the moment of inertia? Mr squared. On the other hand, if I have a hoop, and the axis of rotation is passing through the diameter here, the moment of inertia is half mr squared. Okay. If it was passing through here, the moment of inertia will be mr squared. Now it's passing through the diameter, it will be half mr squared. So what is in your formula sheet, I believe, is the second one. This is in your formula sheet, this one. This one is not in your formula sheet because the axis of rotation is passing through the diameter. Anyway, if you need it, I will give it to you. Now, that's what I have. So moment of inertia of this hoop around this axis of rotation is half mr squared. Now, what is the moment of inertia of the rod around this axis of rotation? Well, a rod, I know the moment of inertia when the axis of rotation is passing through the center of mass. Let's say the center of mass is right here in the middle of the rod because it's a uniform rod. The moment of inertia when the axis of rotation is passing through the center of mass is 1/12 of ml squared. Okay. So here L is equal to 2r. So it will be 112 of m2r square. Okay. Now, if the axis of rotation is shifted from here to here, all what I need to find is this distance h. And the h here will be what? R plus R, basically 2R. So I will apply parallel axis theorem. So the moment of inertia of the rod around this new axis of rotation here, okay, will be equal to the old moment of inertia, which was 112 of ml square. And I know what is L, because L is equal to 2R, plus mh square, and h is equal to also 2R. So I shuffle it and I get the moment of inertia of the rod around the new axis of rotation, which is passing through here, is just 13 divided by 3 multiplied by mr squared. Now I just have to add. And when I add, I find the moment of inertia of my system around the axis of rotation. Okay? It's like the center of mass. If I have a complex geometry, I break it down into simple geometry and I calculate the moment of inertia of each simple geometry around the axis of rotation. And of course, parallel axis theorem is very helpful in this case. Now, second question is I take the same system and I already calculated the moment of inertia. Now I give you R, I give you the mass, but you will see the mass will not be very important. Okay. What is the moment of inertia? Is 29 divided by 3 mr squared, right? 29 divided by 6, sorry. So 29 divided by 6 mr squared. I calculated the moment of inertia of this complex geometry around this axis of rotation. 29 divided by 6 mr squared. Now the question is this. I gave you R and m is a parameter. You will see the m will simplify everywhere. No problem. Okay. But let's say I give you m. Okay. You will not need it here because it will simplify. Now the question that I will ask you is, if I keep this object here in this vertical direction, and let's assume that the racket starts falling down from rest, and then the racket is inverted. The question I will ask you, what is the angular speed when the racket is vertically downward? Because the racket will be rotating around this axis of rotation. Okay? And let's say suddenly it falls down around this axis of rotation. The question is, when it's inverted, what is the angular speed, omega? So that's why I said starting from rest, of course, omega initial is equal to 0. The object rotates around the axis of rotation from its initial upright orientation. So this is the initial upright orientation. Now the question is, starting from rest and the object starts rotating from the initial upright orientation, what is the angular speed omega about this axis of rotation when the racket or the object is fully inverted? Okay, so this is the initially at rest, omega 0 is 0. Now the final situation is when it's downward, okay, fully inverted. And the question is, this is finally inverted, what is this omega? What is omega final, which is equal to this omega when it's downward? So what do you think? We will use conservation of mechanical energy, actually. Now let me justify why we use conservation of mechanical energy, because we have a conservative force. Okay. Only one conservative force is working, which is a gravitational force. This racket is falling and find itself inverted because of the gravitational force, which is working. Now, this is what I said here. Of course, work applied is 0. Okay? The normal force does not work. The normal force from the rotational axis on the object does not work, okay? Because the moment arm is 0. Okay? The radial force, because it's applied on the axis of rotation, which is my kind of origin. So the only force that is doing a work is a gravitational force. Okay? Now, if I take an Earth object system, I will have conservation of mechanical energy. Delta K plus delta UG is equal to 0. Okay? Only gravitational force is doing work. and gravitational force work is embedded in delta UG here. So this is what I will have. I will have delta K plus delta UG is equal to 0. Delta K, it's an object which is rotating. So it will be K final minus K initial. What is K final? Is half I omega square. Omega final is equal to omega. What is K initial is 0 because, you know, omega initial, omega 0 is 0. Now, what is a change in gravitational potential energy plus delta UG? Now, we have to find delta UG. Now, in order to find delta UG here, you see here, I have a complex geometry. If it's inverted, you know, the change in height for each point of my object is different. So here my solution is what? I have to find the center of mass of this complex geometry. Where is the center of mass of this complex geometry? Okay, this is a hoop of mass M, so it's uniform. The hoop, the center of mass of the hoop is right in the middle here. This is a rod, a uniform rod of mass M. The center of mass of this rod is here, right in the middle. Okay, so here's a hoop. I have M, which is right in the middle here. Here I have a rod of mass M right in the middle. Okay, so that means the center of mass of the whole system is just right here in the middle here. Okay, the center of mass is right here. Okay, now what I will see is I will look at the change in height of the center of mass. Okay, so center of mass was here initially. At the distance r forms the axis of rotation. When it's completely inverted, the center of mass is right here. At a distance r below the axis of rotation. So the change in height, y final minus y initial, is equal to what? Minus 2r. Okay, so I had r here, and I have r here. So basically I have 2r, but it's in the below direction. Okay, so delta UG will be equal to what? Basically 2m, which is the total mass, g multiplied by delta y, and delta y is equal to minus 2r, and this is equal to 0. Okay, so this is the equation that I have to solve, and as you can see, I know I. Okay, I is equal to what? 29 divided by 6 mr square. Okay, and I can solve my problem. So if you want me to solve it, I can do it quickly. Otherwise, if you understand what I said, this is it. So this is what I said. Half I omega square plus total mass of the system, which is 2m. Okay, be careful because the hoop is mass m, the rod is mass m. So 2m g delta y. And as I said, delta y is here. Y final minus y initial. Okay, so I will take, of course, this as my reference. So ug is 0 here. Okay, so basically it will be this minus this. So delta y will be minus 2r. So the rest is just simple. You just replace, okay? Half I is 29 divided by 6 mr squared multiplied by omega squared plus 2mg multiplied by 2r. And as you can see, the m goes away, and your only unknown here will be omega. Omega will be 48g divided by 29r. Now you put your numbers, and you get 10 radian per second. So this is a good question, and it's a good question specifically because I have my center of mass I have to locate, and I look at the change in height of my center of mass of the whole system. Okay, and the center of mass of the whole system, as I said, is here. When it's inverted, is here, so the delta H is minus 2R. And don't forget, change in kinetic energy is rotating. It will be half I omega final square minus half I omega initial square. Okay, so we are done for this chapter. Now let me solve a couple of recitation problems in chapter 10 before I stop this video. So tomorrow in lecture, inshallah, I will solve, of course, more recitation problem for chapter 10. So let's look at this problem here. What do we have? We have a fin rod. So let's read it carefully. So we have a fin rod, and I give you the mass of fin rod, and I give you the length of the fin rod. Is pivoted at one end, okay, and can rotate in a vertical plane about that frictionless pivot point. So this is my rod. I know the mass of the rod is ½ kilogram. I know the length of the rod, 2.5 meters, and I put the pivot point at one end here. Okay. Okay, so it's pointing towards you, and this rod can rotate around this pivot point. So the rod is released from rest when the rod makes an angle of 45 degrees above the horizontal. So here I gave you this angle theta, which is 45 degrees. And initial here, my omega initial is 0 because it's released from rest. So the question is, calculate the angular speed of the rod as it passes through the horizontal position. So this is the horizontal position here. The question is, what is omega final? Okay, what is omega? Okay, omega equal omega final. What is omega final when the rod is passing through this horizontal position? First thing first, what do I need to do? Here, I have a conservative system, okay? So here, the only work which is valid is the work of gravitational force. The work of the normal force from the pivot point is 0 because the torque of the normal force is 0. So I have also, like in the previous example that we just solved, I have conservation of mechanical energy. So what does it mean? It means I have delta K plus delta UG is equal to 0. Now what is delta K? Is K final half I omega final square minus half I omega initial square, which is 0, okay, because omega initial is 0, as we said, plus delta UG. Now, what is delta UG? Of course, it's going down. It will be mg delta y, right? Y final minus y initial. And this should be equal to 0. Now, again, what is delta UG or delta y? Here I have a rod. So it's like the previous example. I have to first locate the center of mass. It's a uniform rod. The center of mass is here, right in the middle. Okay. So now I will look at the change in height of the center of mass. The center of mass was somewhere here. Now it ended up here. So the change in height is this h. Okay. Now I have to find the h. Okay. So how should I find h? So if this angle is theta here, okay, this is half L because the total length is L. So I have sine theta is equal to h divided by half L. So that means h, which is my change in height, is just equal to what? L divided by 2 sine theta. Okay, so this h is here, and it's the same here. Okay, I have a triangle which is rectangle, of course. So if this is theta, this is half L, and of course this is h, and this is 90 degrees here. Okay, so delta y final minus initial, delta y is just minus h. which is minus L divided by 2 sine theta. Now let's go back to my problem. I need to find also the moment of inertia. What is the moment of inertia of this rod? Well, we studied this in class. Okay, if I have a rod of mass m and length L, the moment of inertia when the axe of rotation is passing through the middle is 1/12 of mL square. Here, I shifted the axe of rotation to the pivot point here. Okay, so I shifted the axe of rotation at the pivot point. So what is the new moment of inertia? Parallel axis theorem. Okay, so the new moment of inertia is the old moment of inertia, 1/12 of mL square plus mh square, but h here will be L divided by 2. And we did this many times. Okay, if you do it, you will find 1/3 of mL square. Bottom line, when the axe of rotation is passing through the middle, it's 1/12 of mL square. When it's passing through the one extremity of my rod, it will be 1/3 of mL square. And we already demonstrated this in class. Okay, so I will come back to this equation. I will have 1/2. Here I will have 1/3 of mL square. So this is I. Now omega square is equal to, okay, minus mgh, but h will be minus L divided by 2 sine theta. Minus minus goes away. You see the m will simplify. So I did not even need to give you the m. The half will simplify. Okay, this L square and this L will simplify. I will end up with omega square is just right. So I'll have 3g sine theta divided by L, and then I take the square root. So this will be my omega. Okay. So this will be my angular speed when I am right passing through the horizontal position. Okay. So that's what I explained here. Okay. So this is what I explained here. This is what I explained. This is what I explained already. Okay. So this is 1/3 of mL squared, the new moment of inertia, and this will be equal to mdh. H is equal to L divided by 2 sine theta. And then you get this, you put your numbers, and you get 2.88 radian per second. Okay. Good. Now, the next question is, what is the linear speed of the center of mass? Now I know the angular speed, omega. What is the link between the linear speed and the angular speed? The linear speed V is just R omega, R being the distance between the point I'm looking at and the axe of rotation. So here, the linear speed at the center of mass is R at center of mass multiplied by omega. So here the whole rod have the same angular speed. So here, omega, because it's a rigid body have the same angular speed, okay? So here, each point of my rigid body have the same angular speed. So when I pass through the horizontal, this omega final is the same as omega is 2.88 radian per second square. And this is the same for all of them. But now the linear speed will depend on the position, okay? So here, when I'm looking at the center of mass, the R of center of mass is the distance between the center of mass and the pivot point. And that will be half L. So it will be half L multiplied by omega, okay? So this is why, what is the linear speed of a point at the pivot point? It will be 0, because V at the pivot point O will be R O multiplied by omega, but RO is 0, okay? What is the linear speed of a point which is at the other end of my rod? V will be R omega. But for this point at the end of my rod, the R is the distance between the point at the end of my rod and the pivot point, basically L. It will be L omega, okay? So if you take your calculator, you can calculate what is the linear speed of the center of mass of the rod. And also you can calculate what the linear speed of the other end of the rod, okay? The linear speed for the pivot point is of course 0. Omega is not 0, but the distance between the pivot point itself is 0. So if you do it, you get it here, okay? Here, I already said it. Remove this. Okay, you have omega multiplied by L divided by 2. So this is the R, which is L divided by 2. So you get 3.6 meters per second. That's a linear speed. Okay, now let's go to the next problem here, which is pretty the same. Okay, I did exactly the same thing. I have a rod. Now my initial position is the horizontal, and it's released from rest. Omega initial is 0. The question is, what is omega final when it's vertical? And again, the pivot point is right here. Okay, so I will have delta K plus delta UG is equal to 0. Delta K will be half I omega square. Okay, and delta UG will be mg, delta y. So y final is here. I look at the center of mass. Okay, it's a uniform rod. The center of mass is right here in the middle, right here in the middle. So what is the change in height here? Okay, so if I take this UG as my 0, here I'm going below, so it will be mg minus half L. This h here is just half L. So final, which is here, minus UG initial is just half L. Okay, so mg L divided minus L divided by 2, and this is equal to 0. Okay, so I will have half I. What is I? It's a rod, so it's 1/3 of ml square is equal to mg L divided by 2. So L goes away here, so I have one L, half goes away. Of course, here I forgot my omega square, so I end up with omega is just square root of 3g divided by L, because the mass will simplify, of course. That's why I did not give you the mass. Okay. And then you get your right answer, which is right here. Same thing. I hope it's clear, okay? So this is what I did here, and that's it. Okay. Good. Now the same problem happens here. I just change the shape of my object. Here I have a uniform disk. It's a solid disk. Okay. And I give you the mass of the solid disk and the radius of the solid disk. Okay. And it's pivoted around an axis which is passing through one edge. So my initial position is here. And my final position is here. So I release it from rest. My initial position is here. Omega initial is 0. Okay. And the question is, what is the speed? When I say speed, I'm talking about linear speed of the lowest point of the disk as it passes through the vertical final position. Okay, so it's vertical. Okay. So at the beginning, it was like this. My disk, I release it from rest. It rotates downward, and this is my final position here. The question is, what is the speed of the lowest point? What is V here? Okay. Of course, V here will be R omega. R being the distance between this point and the pivot point. So R here is 2 times the radius. So V will be 2 times the radius multiplied by omega. Okay. Now the question is, what is omega? Well, that's what I have to calculate. Again, I will have delta K plus delta UG is equal to 0, because here I only have conservative forces that are doing work, okay? The normal force at the pivot point is not doing work. And there is no friction, so I have a conservative system, because I said it here, frictionless spin, okay? So delta K will be half I omega final square, which is this omega, basically the omega when I reach this final position. Well, omega initially is 0, so minus 0, plus delta UG. Now what will be delta UG? Okay, so I have to locate the center of mass. The center of mass, it's a uniform solid disk. It will be right here in the middle. And finally, the center of mass is somewhere here. So the change in height of the center of mass is just what? What do you think? Of course, R. Okay. So plus delta UG, of course, is going downward. Final minus initial, because final is smaller. So it will be plus mg multiplied by minus R. And this is equal to 0. Okay. Well, here small m is capital M, because here I call it capital M. Okay, so let me put it here, capital M, just for you. But you know that it will simplify. Now, what is this moment of inertia I here? I will use parallel axis theorem. When I have a solid sphere, no, sorry, a solid disk, and the axis of rotation is passing through here, what is the moment of inertia? Formula sheet, 1/2 of mr squared. Now, what about when the axis is shifted from here to here? Okay, and it's both axes are coming towards you. So the new moment of inertia, parallel axis theorem, is the old moment of inertia, which is 1/2 mr squared plus mh squared, and here h is equal to r. So the new moment of inertia will be 1/2 mr squared plus mh squared, h is equal to r squared. So at the end of the day, I'll find the moment of inertia 1/2 plus 1 mr squared. It will give you 3/2 of mr squared. Okay, so that's it. So I will have 1/2 multiplied by 3/2 of mr squared is equal to mgr. Okay, so the m will simplify, of course. Okay, so I will end up with, well, here I forgot about omega. Of course, it's 1/2 I omega squared. Okay, here I forget about the omega squared. And here I forget about the omega squared, of course. Be careful, okay? So you will end up with omega is just square root of 4g divided by 3r. And once I get omega, well, v is easy. I will have v will be just equal to 2r multiplied by omega, which is square root of 4g divided by 3r. And you get the numbers, it will give you 9 meters per second. Okay, so finding the omega is the same, we have the same procedure, okay, in the 3 or 4 exercises that I just solved now. Okay, you use this, you know that delta K will be 1/2 I omega squared. This I have to locate the center of mass, and I look at the change in the height of the center of mass. So it will be mg here, it will be just minus r, because this h is just r minus, because final is below, of course, that's why I have a minus. Okay. So I get it using parallel axis theorem. Okay, easy, and then the rest is just history. Okay, so tomorrow we will finish solving this recitation problem, and then I will upload them, inshallah, on Blackboard. So see you tomorrow. I will record and upload both videos on Blackboard. Thank you. Assalamu alaikum. So Bismillah ar-Rahman ar-Rahim. So today we will solve recitation problem for chapter 10. So yesterday we finished chapter 10. Tomorrow we will start chapter 11, inshallah. So let's solve problem for chapter 10. So again, I'm recording this session. You can watch it whenever you can, but please take notes, okay? So yesterday I recorded a video that I already posted on Blackboard, and we solved this problem here. So this problem is in the slides, and I explained it extensively in the video that I already posted, okay? So this problem is the follow-up of the previous problem. Please watch it out. This is a very important problem, okay? This problem is roughly the same. And again, I solve it in the video that I posted online. You can watch it out. This problem as well is roughly the same, and I posted online. I solved this problem as well, and I posted it online. So watch the video that I already posted on Blackboard. Okay, so let's start directly from here. So let me remind you a couple of important concepts. The concept of moment of inertia, of course. You know the moment of inertia of a rigid body. I will give you the formula sheet. Okay? In the formula sheet, I will give you a couple of 4 different momenta of inertia. Okay. So the first one I want you to remember is when I have a solid cylinder or a disk, and the axis of rotation is passing through the center of mass here. What is the moment of inertia of this disk? 1/2 of mr square. M is mass of the disk, r is the radius of the disk. Now my question is, what happens if I shift the axis of rotation here? And I call this axis axis 2. What is the moment of inertia around axis number 2? What do I have to apply in order to get it? Parallel axis theorem. The moment of inertia around the new axis of rotation, which is parallel to the old axis, is the old moment of inertia plus mh squared. And h is a distance between these two axes, a perpendicular distance. So here h is equal to r. So in other words, it will be 1/2 mr squared plus mr squared. And the new moment of inertia around this axis is just 3/2 of mr squared. Okay, mr squared, 1/2 mr squared plus mr squared gives you 3/2 of mr squared. And this is a parallel axis theorem, extremely important. Okay. The formula sheet will give me the moment of inertia around an axis passing through the center of mass. I can know the moment of inertia around any axis parallel to that axis by using the parallel axis theorem. A rod. I have a rod of mass capital M and length L. And I have an axis of rotation which is passing through the middle, through the center of mass. And my object is rotating this way. And of course, the axis of rotation is perpendicular to the rod. So what is the moment of inertia of this rod with respect to this axis passing through the middle of the rod, perpendicular to the rod? It will be 1/12 of ml squared. It's in your formula sheet. Now what happens if I shift my axis at the one end of the rod? Okay. So the h here will be what? L divided by 2. Basically the distance between the two axes. So my new moment of inertia, let me call this axis axis 2, is the old moment of inertia, 1/12 of ml squared plus mh squared. M is the mass of the whole rod. H here, as I said, is L divided by 2 square. And if I do it, I find 1/3 of ml squared. So this, I want you to know it by heart. Okay. It will solve, you will gain 30 seconds or 10 seconds. When I have a rod, the axis is passing through the center of mass perpendicular to the rod. The moment of inertia is 1/12 of ml squared. When the axis of rotation is passing through one end, the moment of inertia is 1/3 of ml square. Now let me ask you a simple question. Let me take the same rod, same mass, same length. Now, if I put the axis of rotation on the rod, so what is the new moment of inertia around this axis of rotation? Anyone? Nasser, Muhammad, Ibrahim? Hussein, what do you think? Osama? Or anything? Okay.
ML.
You think it will be ML? Moment of inertia should be m multiplied by a distance square. So it should have a distance square somewhere. Actually, it will be 0. Why? Because I have my rod here. It's here, right? And a rod by definition is a one-dimensional object. Okay. As I said, in a rod, this width, or let's say, diameter of the rod is very small compared to the length. So the rod is one-dimensional. So if I take the axis of rotation and I put it at the same, in the same direction as the rod, the moment of inertia is 0. Why? Because I took the whole mass of the rod and I focus it at the axis of rotation at the distance 0. You remember that moment of inertia, if I have a solid body, is an integral of r squared dm. Now, in this rod, with this axis of rotation, I took the whole mass and I put it at exactly r equal to 0, basically at the axis of rotation. So the moment of inertia of this rod, and the axis is passing, let's say, through the rod, like in the same direction, the moment of inertia is 0. Do you agree with me?
Yes.
Okay. So if you disagree, just say it, okay? Now, for a solid sphere, of course, is 2/5 of mr squared. A solid sphere, as I said, the mass is uniformly distributed in the sphere. Okay, it's a full sphere. So it's 0.4 mr squared. For a thin spherical shell, which I call also a hollow sphere, so the sphere is empty inside, the whole mass of the sphere is focused at the external radius. Inside, it's empty. So it's 2/3 of mr squared. And as you see, it's 0.667 mr squared. And it's larger, as I said, okay, because I'm maximizing the r here. Now, I will use parallel axis theorem. Now, let me choose an axis here, which is passing through this. And let me call it axis number 2. Okay. And of course, the h here is equal to what? R. So what is the moment of inertia of this solid sphere with respect to the new axis of rotation 2? Calculate it at home. It's parallel axis theorem. Now the same thing for the hollow sphere or the thin spherical shell. What is the moment of inertia of this thin spherical shell? If I shift my axis of rotation from the diameter to tangentially to one end. Okay, so h here is r. Okay, and my object is rotating this way. You can calculate it using parallel axis theorem. Second thing I want to remind you is about kinematic equation for a rotational motion under constant angular acceleration. Omega final is omega initial plus alpha t, if alpha is constant, of course, and these things. Okay? They are very important. They're in your formula sheet. Okay, now let me go to the next slide. So this is a reminder of what I talked about. Let me just focus on the hoop here and here. You see the hoop here, the axis of rotation is passing through the central axis here. Okay, so the hoop is rotating this way. Okay, it's rotating around this axis of rotation. So what is the moment of inertia of this hoop? By the way, a hoop is a ring. Okay. The whole mass is focused at the radius r, and it's empty, of course. Okay. So the hoop about its central axis, the moment of inertia is what? mr square. And this is in your formula sheet. If you look at the formula sheet, I put moment of inertia of a hoop, and I said mr square. I mean the axis of rotation passing through the central axis. Now I take a hoop now, and now the axis of rotation is passing through the diameter. What is the moment of inertia of the same hoop, same mass, same radius, but the axis is passing through the diameter? It's half mr square. Okay. And this is not in your formula sheet. This one is in your formula sheet. This one is not in your formula sheet. So if you need it, I will give it to you. Okay. And I told you how to get this. All of these are coming from an integral. Those who are doing Math 102, you know, a double or triple integral, I believe, or Math 201. You will study this. Okay. But for the moment, yeah. And here, of course, you cannot use parallel axis theorem from here to here because these axes are not parallel. They are perpendicular. Okay. So here I can use parallel axis theorem if my axis is passing through here. Here I can use parallel axis theorem with respect to this if my axis is passing through here. Between this one and this one, I cannot use parallel axis theorem because they are perpendicular. Okay. You use parallel axis theorem when the axes are parallel to each other. Okay, good. So that's a kind reminder. Now let's solve problems. We will start slow and then we'll go faster and faster and faster, constant angular acceleration. Okay, so let's see who can read this problem. Or let me read it. So here I have T-shaped objects. Each of these T-shaped objects shown in the figure below is made of two identical uniform rods. Again, a rod is one-dimensional. Uniform, I mean the center of mass is right in the middle. So the rods have the same mass and same length. Okay, so each of them has this shape, a T, inverted T, let's say. Okay. So this rod here, I will call it 1, and this rod here, I will call it 2. Each of them have the same mass, same length. Okay, so the total mass is 2m. So each object is rotated about an axis of rotation indicated by the dotted line. So here, this is the axis of rotation. Here, this is the axis of rotation, and etc., etc. Okay. So which one of these objects has the largest rotational inertia? As we said, rotational inertia is the same as moment of inertia, I. So which one has the largest rotational inertia?
A.
Yes, thank you very much, Hussein. It's given here, A. Now why?
The distance.
Okay, so you see all of them have the same mass. Okay? All of them, you know, it's the same object. Now the thing is, you know that moment of inertia, if I have identical, let's say discrete particle, is just sum of mi ri square. Okay, each particle is at a distance. So this is my axis of rotation. I have a particle here, I have a particle here. I'm looking at this. So this is particle 1, this is particle 2. I'm looking at the distance, perpendicular distance, of course, between the particle and the axis of rotation. This is R1 and this is R2. Okay. If I have a solid object, I will have an integral of R squared dm. So as I said, you have the mass, but how you distribute the mass around that axis of rotation. So here, I have the same mass, but I will distribute it differently from the axis of rotation. So the further I distribute it from the axis of rotation, the larger the moment of inertia will be. So in A, I took everything and I put it in one side. So it will be larger. In B, no, because, you know, I took one, the axis of rotation here is here. So it will be less. Here, of course, it will be less. Here, you can say, oh, it should be less or more, but it will be less. because, you know, this distance is the largest distance I have. So A will be the greatest moment of inertia. If I am to ask this problem, this is too easy. I will say rank them greatest first. So which one is the greatest? As we said, it's A. Which one is the second greatest?
D.
D. Then
Yes.
yes, I agree. So A is the greatest. Then D.
Then B and C.
B
Then
equals
B.
0.
Then B. Then C. Yes, this is correct. B is not equal to C, the moment of inertia. So let's calculate each moment of inertia and you will enjoy the process. So as I said here, each T-shape is made of two parts, 1 and 2. So the total moment of inertia is just I1 plus I2. Okay. So let me calculate for the first one, IA. What is the moment of inertia of 1? This is part 1. It will be 1/3 of ml square. Why? Well, I have my axis of rotation here. I have my rod here. Parallel axis theorem. This is exactly what we talked about. Okay. It will be this case here, 1/3 of ml square. So A1 will be 1/3 of ml square. What about this part, which I call 2? So this is 1 and this is 2. What is A2? I will use parallel axis theorem as well. Because when the axis of rotation was passing through this rod, the moment of inertia will be 0. So when the axis of rotation is passing through this rod, the moment of inertia is 0. Now, if I shift it to this distance L, the new moment of inertia will be 0 plus mh square, but h is equal to L. So it will be ml square. So I will end up with 1/3 of ml square plus ml square. It will be 4/3 ml square. Okay. This is for A, moment of inertia of A. Okay. Now let's go to the moment of inertia of B. Now the axis of rotation is passing through here. So moment of inertia of B will be moment of inertia of this one here, which is the same 1/3 of ml square. Now what is the moment of inertia of part 2 here?
0.
Thank you very much. Okay. Because if I have a rod, and of course the axis of rotation is passing along the rod, the moment of inertia is 0. So moment of inertia of B is just 1/3 of ml square, of course. C, what is the moment of inertia of C? So 1, this is 0, because the axis of rotation is passing along my rod. Plus, now for this one, the axis of rotation is passing through the middle, so it will be 1/12 of ml square. So AC is equal to 1/12 of ml square. Now finally for D, what is the moment of inertia of D? Okay, so for 1, if I put my axis here, it will be 0, and then I shift the axis here, so H is equal to L divided by 2. So A1 will be, no, I1 will be 0 plus M L divided by 2 square. Okay, parallel axis theorem. Now let me calculate the moment of inertia of this part here. It will be what? Muhammad? Hello?
Like 1/3.
Okay, so you will, even if it's obvious, you can say it, okay? Physics is obvious anyway, but I want it to be participative. So we will have 1/4 of ml square plus 1/3 of ml square, that will give you 7/12 of ml square. So you see that moment of inertia of A is the greatest, then moment of inertia of D, then moment of inertia of B, then moment of inertia of C, as Hussein guessed at the beginning. Okay. Now, let's go to the next problem. Is it clear? Why calculating moment of inertia is very important? Because I will be calculating kinetic energy. Kinetic energy is half I omega square. So if I calculate I correctly around the axis of rotation that I want, I will get the kinetic energy. But also I know that Newton's second law for an object which is rotating, net torque is I alpha. Net torque around the axis of rotation is moment of inertia around that axis of rotation multiplied by the angular acceleration around the same axis of rotation. So I have to be able to calculate properly the moment of inertia around the axis of rotation, the axis of rotation. Okay, now let's look at this problem here. So this problem is almost the same, not very difficult. So we have a rigid structure consisting of a circular hoop, okay, of radius r and mass m. And then a square made of 4 fin bars. You see, this square is made of 4 fin bars. And each bar has a length r and a mass m. So the rigid structure rotates at constant speed about the vertical axis. And you see, this is the rotational axis, this vertical axis, with a period of rotation of 2.5 seconds. Capital T is 2.5 seconds. I give you the value of R, I give you the value of M. I ask you to calculate the moment of inertia of the whole structure around this axis of rotation. And the second question is find the kinetic energy, the rotational kinetic energy. Okay. So let's find the moment of inertia of this whole structure. So this structure or this system is made of a circle plus 4 sides of a square. Okay. Basically, each side I will call it 1. This side I will call it 1. This side I will call it 2. This side I will call it 3. And this side I will call it 4. So the total moment of inertia of my structure or of my system will be the sum of the moment of inertias. It will be moment of inertia of the circle around this axis of rotation plus the moment of inertia of part 1 of my square, part 2 of my square, part 3 of my square, plus moment of inertia of part 4 of my square with this axis of rotation which is fixed. Now, what is the moment of inertia of my circle? I already talked about it. If the axis of rotation is passing through the diameter of my hoop or my ring, the moment of inertia is what? Formula sheet, half mr squared. So if I shift the axis here, and I shift it by a distance h, which is r, so the new moment of inertia, I of the circle, I apply parallel axis theorem plus mh squared. Okay? So it will be 1/2 of mr squared plus mr squared because the shift is r. So this gives me, as I said at the beginning of the class, 3/2 of mr squared. Now let's calculate the moment of inertia of this gentleman here. 1. What is I1? 0, because the axis of rotation is along the rod. So what is I3? So this is 1 here. This is 3. For 3, I can apply parallel axis theorem. It will be I1, which is 0, plus h, and the distance is here r. So r squared. So it will be 0 plus mr squared, which is mr squared. Okay, be careful here because it's a small m. We all call them small m. So I am putting capital M, but it's lowercase m. Okay? So I1 is 0. I3 here is equal to mr squared. Now I4, no, or I2 is equal to I4. This is 2 and this is 4. And what is the moment of inertia of 2 and 4 with respect to this axis of rotation? Should come very quickly. Okay, it's 1/3 of mr squared. So you add all of them and you will get 29 divided by 6 mr squared. You put the numbers, you will get the right moment of inertia in the right units. Now the second question is, what is the kinetic energy? Once I get the moment of inertia, the kinetic energy is just half I omega squared. I know I. Now what is omega? I know that omega is 2 pi divided by t. So it will be 2 pi divided by 2.5 seconds. Okay? And this will be in radian per second. Okay? Because I gave you the period of rotation t is 2.5 seconds. So you know that the angular speed is 2 pi divided by the period. So I plug it here and I get my kinetic energy. Any question about this? If I give you this in the major exam, full mark, inshallah. Okay, great. So this is what I did here, and the moment of inertia will give you 1.6 kilogram multiplied by meter squared. The angular speed is given, and you just use K is half I omega squared. Okay, now let's solve this problem. So this is the Atwood machine. You remember we studied about the Atwood machine when the pulley was massless. Now I will study about the Atwood machine if the pulley has a mass and a radius. So here M1 is given and M2 is given, and M2 is bigger than M1, as you can see. M1 is 0.46 kilogram, M2 is half kilogram. So what does it mean? If I have this one will move up, this one of course will move down, and my pulley will rotate clockwise in the negative direction. Okay. I will not solve this problem exactly, but I will give you the general problem. And then, inshallah, this problem will be just, you can solve it quickly. Now, let's do. So let's say, for instance, I give you this Atwood machine. Now the pulley has a mass. Let's say it has a mass M and radius R. I did not really give you the moment of inertia. I did not say that it's a disc, or it's a cylinder, or it's a hoop. Okay, we will see. Let's just call its moment of inertia, let's call it I. And in general, I here will be alpha multiplied by mr squared. Alpha being a number, okay, between 0 and something. Okay, sometimes it will be half, sometimes it will be 2/5, sometimes it will be 2/3, depending on the nature of my pulley. But let's just say that I give you the moment of inertia I, and I give you the mass M1, and I give you the mass M2, and M2 is bigger than M1. So that means, of course, M1 is moving up, the pulley is rotating in the negative direction here, and M2 is moving down. Now let's just calculate the acceleration. What is the acceleration of block A and block B? What is the acceleration of M1 and M2? In order to do that, let's do a free body diagram on my system. You are in dynamics, always you draw a free body diagram. So let me start by block 1. Of course, I have the weight of block 1, M1G. I will have here what I will call tension 1, T1. Okay, and I will have the acceleration which is moving upward. For tension 2, for block 2, I will have M2G, and I will have T2. Okay, and I will have the acceleration moving downward. Now I have to do a free body diagram for the pulley. If the pulley is massless, I don't need to do a free body diagram for the pulley because the pulley is just here to connect. But now we know about rotation, I have to do a free body diagram on the pulley and apply Newton's second law to the pulley. So here, for the pulley feels that there is something holding his back here. So he will feel T1 downward and feel T2 downward as well, but in the opposite direction in terms of torque. Okay. Good. Now, let me do Newton's second law on block 1. So on block 1, I will have plus T1 minus M1G is equal to M1A. Okay. So this gives me T1. It's just M1G plus M1A. Now let me apply Newton's second law on block 2. On block 2, I will have what? Plus T2 minus M2G is equal to minus M2A. That means T2 will be equal to M2G minus M2A. Okay. The problem is I don't know A yet. Okay. If I know A, I will know what is A, T1 and what is T2, but I don't know A yet. Now let's get A. Okay. I'm not solving this problem. This problem, I already gave you A because, you know, we'll talk about it. This will give you A. Once I get A, I can get T1 and T2, and then I get the rest. But here, I'm just solving in general. I want A. I don't know A yet. Okay, good. So here, let me say something. This A is in magnitude, right? Because the minus is already put out here. So A is positive here. Okay, A is positive. Now, I apply Newton's second law on this block. Now I have to apply Newton's second law on the pulley. The pulley is an object which is rotating, so net torque is I alpha. This is Newton's second law for an object which is rotating. Now, what is a net torque? Of course, the net torque will be torque of gravitational force plus torque of normal force plus torque of T1 plus torque of T2. And this is equal to I alpha. So the pulley has a mass, so the pulley has a gravitational force downward. And the pulley has a normal force because it's, you know, attached here, or it's fixed here, so the normal force is here. But these two forces are radial forces. The moment arm is 0. So the torque of the gravitational force is 0. The torque of the normal force is 0. They are not participating in the rotation of my object. So only T1 and T2 are effectively rotating my pulley. Okay. Now, here, let me tell you the general thing and I'll give you the shortcut. Okay. So here you know that the pulley is rotating in the clockwise direction, in the negative direction. So that means I know that alpha should be negative. Okay. So let me say that this is equal to I alpha, but I know that this alpha is negative. So you see, let's calculate the torque of T2 first. So T2 will make my object rotate in the negative direction. So I will have minus T2 multiplied by R. Why? Because here you have 90 degrees between the R, the vector position, and the tension in my pulley. Okay? So minus because it makes my object rotate clockwise in the negative direction. On the other hand, T1 will make my object rotate with respect to the rotational axis, which is here in the middle. Will make my object rotate counterclockwise. So the torque for T1 will be plus T1R. Okay. Plus because it will make my object rotate in the counterclockwise direction. And here you have 90, it will be plus T1R. But here you see, I will have what? I will have T1 minus T2 is equal to I alpha divided by R. Okay. But here my alpha will be negative. Okay? Because I know that in reality, my pulley is rotating in the negative direction. Okay, this is one way, or this is the way that we can use. But I will not prefer this way. What I will prefer is this. I will say, okay, my object is rotating in this direction, in the negative direction. What does it mean? Okay, it means that the torque, my object will always rotate in the direction of the dominant torque. So my object is rotating, this pulley is rotating this way, so the dominant torque is T2. So I will say T2R, which is a torque of T2. I say plus because I'm looking in the direction of rotation. Okay, and the other one is negative, minus T1R is equal to I alpha. But if I say this alpha is positive. Why? Because I'm looking in the direction of rotation. Okay? So the dominant torque is T2R, and it's bigger than T1R. Okay? So that means that this alpha is positive. Okay? So I will have what? T2 minus T1 is just I divided by R alpha. But now this alpha is a positive number. Forget about this one. Okay? Here alpha is negative. Now this is my equation here, second equation. Now I have a link between this alpha and this A. Okay, so the link is the acceleration of the block in magnitude is equal to the absolute value of the tangential acceleration of my pulley. In other words, the acceleration of the block in magnitude is equal to R multiplied by the angular acceleration, because the tangential acceleration is just R alpha. But here I'm talking about alpha positive. Okay, so that means alpha is just A divided by radius of the pulley. So now I will put it here. So I will have T2 minus T1 is equal to I divided by R. Instead of alpha, I will say magnitude of the acceleration divided by R. So I'll have A divided by R squared. Now TU2, I already get it from here. T1, I will already get it from here. So I can plug T1 and T2. So if I do that, what I will have is this. Okay, so T2 will be M2G minus M2A minus T1, which is M1G minus M1A. This is equal to I divided by R squared multiplied by A. Let me put the A's together and put the G's together. So because I want A, right? So A is my unknown. Okay. Did I forget an A here? Yes, this is an A instead of G. Okay. So we will have what? We will have A is equal to M2 minus M1 divided by M1 plus M2 plus moment of inertia divided by R squared multiplied by G. So this is my acceleration. This reminds you something, right? We used to do this, but when the pulley was massless. So if the pulley is massless, we used to have I is equal to 0. And we used to have that acceleration is M2 minus M1 divided by total mass multiplied by G. If the pulley is massless, I is equal to 0. And again, if the pulley is massless, I is equal to 0. That means this is equal to 0. That means T2 minus T1 is equal to 0. That means T2 is equal to T1, as we used to say when we used to have a massless pulley. We used to say that the tension here is equal to the tension here. But now the pulley is not massless anymore. The pulley is rotating. So it has a moment of inertia. So the pulley is favoring the rotation in one way. Okay. So, and always, 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 the pulley is rotating in the direction of the dominant torque. So the tension in T2 is bigger than the tension in T1, because otherwise the pulley will not rotate in that direction. Okay. So now once I get A, I want you to write this down. Now things are easy. Once I get A, I go to T1, I substitute A and I get T1, and I substitute in T2 and I get T2. Okay. Now, let me just now summarize what I said in this problem. In this problem, things are easy. I already told you that block 2 is falling down by this in 5 seconds. And of course, the cord is not slipping. So that means I gave you delta y and I gave you time. Okay. So you know that if the acceleration is constant, and we already found that the acceleration is constant, is m2 minus m1 divided by m1 plus m2 plus moment of inertia of the pulley divided by r squared multiplied by g. Of course, the acceleration has the same dimension as g, but I have to take into account this ratio here. So the acceleration is constant. So if I have constant acceleration, delta y will be just half a t squared plus v naught t. But v naught, I said it because release from rest, v naught is 0. So I gave you delta y, I gave you t squared, so you can get a. Okay. Now here, I gave you a directly by this sentence. Once you get a, you can go to t1. You will say that t1 minus m1g is equal to m1a. And you get t1, okay, because now I know a. And then you can get t2 as well. Okay, that's the second question. The first question is, what was the magnitude of the acceleration of the block? You use it, calculate it using this. Then the tension, you use Newton's second law on block 1 and block 2, you get the tension 1 and tension 2. Okay. Once I get the tension, I ask you what is the magnitude of the pulley angular acceleration? Well, you will say in direction, in reality, the pulley is rotating in the negative direction. But that's why I'm saying magnitude. Now, magnitude, you will say that the acceleration of the block is equal in magnitude to the acceleration of the tangential acceleration, which is r alpha. So that means the angular acceleration, alpha, is just the magnitude of the linear acceleration of the block divided by r. You know a, you know the radius because it's given here, 5 centimeters, you put it in meters, you get alpha. Now, once you get alpha, he's asking you what is the rotational inertia. Well, you will say that net torque is I alpha. Okay. So that means I is net torque divided by alpha. I know alpha. Now, what is net torque? Net torque, you will know it. Okay, because it will be T2R minus T1R. I calculated T2 and T1 and I know R, so I divide by alpha. So that's what I did here. Okay. So here the alpha gives you this. As I said, block 1 is moving up, block down is moving down, and this is rotating in the negative direction. And you see here, T2 is 4.87 Newton, and T1 is 4.5 Newton. As I told you, the tension is always bigger in the direction of rotation of my pulley. So the tension is bigger here. Okay. Good. And as you see, T2 is 4.8 or 4.9. Here is 4.5. And you see, this is what I talked about. You get the alpha, and you know T1, you know R, you can get the moment of inertia. Now, you get the moment of inertia, I can ask you, oh, is it a cylinder, is it a pulley, or is it something? So I will give you, basically, you will find it will be beta mass of the pulley multiplied by R squared. So if I know the radius of the pulley, I know the mass of the pulley, I can get beta. And if beta is 1/2, that means my pulley has which shape? Hello. The pulley will have a shape of a disc. Okay. Is it clear? or not really? Hello.
Not really.
What is not clear?
Why put the T greater than T1 and put
Okay.
the alpha is positive?
Okay, good. Now what we will do is, please, next time, if it's not clear, you can interrupt me. Don't wait until I ask if it's clear. Okay? Don't hesitate. Okay? Let's solve this problem. Here it will be, I hope, even clearer. And I hope to, subhanallah, I want to solve all this problem. We will see. Okay, so let's look at this problem here. I have M1, 5 kilogram, and M2 is equal to 4 kilogram. So M2 is on a horizontal frictionless surface, as shown in the figure below. The pulley, I give you the radius of the pulley. It rotates about a frictionless axle. Now, if the acceleration of M2 is 3.5 meters per second square, what is the moment of inertia of the pulley? It's the same problem. So let's do a free body diagram. On M2, you will have a tension here. Let me call it tension 2. That's it. Of course, you will have the gravitational force, normal force, they will cancel. So T2, M2 is moving in this direction with an acceleration which is positive and is equal to 3.5 meters per second square. M1, I will have the gravitational force, M1G, and I will have the tension here. The tension will be, I will call it T1. Okay. And the acceleration is, of course, moving downward with a magnitude of 3.5 meters per second square, because these two blocks will have the same acceleration. Okay. Now, let me apply Newton's second law on block 2. On block 2, I will have T2 is equal to M2A. I will put it small, okay? But you know that it's capital M, basically. Okay, this is Newton's second law on block 2. Newton's second law on block 1, you will have T1 minus M1G will be equal to minus M1A. That means T1 is just M1G minus M1A. So I have my two equations. Okay. Now let me apply Newton's second law on the pulley. The pulley is here. Now the pulley will feel a tension this direction, and this will be T2, and the pulley will feel a tension down here, which is T1. Okay. So the pulley is rotating in the negative direction. So normally alpha should be negative. Okay. But let me apply Newton's second law on the pulley. I will have net torque on my pulley is I alpha. Now what is I? That's a question. Net torque along the pulley, alpha is negative normally. So I can say that it will be the torque. So net torque will be torque of T1 plus torque of T2. This is equal to I alpha. What is torque of T1? Torque of T1 is here. So it will be minus T1R. Why minus? Because T1 will make my object rotate in the negative direction. T2 have a tendency to make my object rotate in the positive direction. So I'll have plus T2R. And this is equal to I alpha. Okay. Here I know this because alpha is negative. Okay. I can use it as this. I don't mind. But here, when I use it as this, as what Hussein wants me to use, which is correct. But here I just need to know that this alpha should be negative. Okay. Because the dominant torque is the torque of T1. That's why my object is rotating in the negative direction. So this torque here is dominant in absolute value compared to this torque. So overall, this one, my alpha will be negative in the same direction as the dominant torque. Okay, but here now, since here A is positive, because A is the magnitude here, A here is positive, but alpha is negative. That means if I say that A is equal to AT, okay, in magnitude, this is equal to R alpha absolute value of alpha. So that means absolute of value of alpha will be A divided by R. Okay, absolute value of A divided by R. But in reality, since I know that A is positive, alpha, and I know that alpha is negative, so that means alpha should be minus A divided by R. Okay? So this is the minus where it's coming from, because I know that for real, alpha is negative and A is positive. So alpha should be minus A divided by R. If I want to avoid this minus, what I have to say is let's keep it as it is, okay? Let's keep it as it is. Okay, alpha is A divided by R. So basically here, I will have what? Minus T1 plus T2 is I divided by R multiplied by alpha. But alpha will be what? Minus A divided by R. So bottom line, I will have minus minus. This minus will go here. So here I will have plus and minus. So I will have T1 minus T2 is I divided by R square A. Okay. What time is it? Oh, subhanallah, time is finished. Okay. So, but you know what I want to do now. I know T1, I just plug it here. I know T2, I just plug it here. Okay. And the only unknown is this one, because I know the acceleration in magnitude is 3.5. Okay. And then I know M1 and I know G, and I know M2 and I know G. So the only unknown will be I, which is a moment of inertia. If I do it, things are easy. Okay. But be careful, because you, Hussein, you want me to use this, I will have to put a minus here. Okay. If I don't want to use a minus, it's simple. I just have to say that since this is a dominant torque, I will have T1R minus T2R, but this is dominant, is equal to I alpha. In reality, now here alpha should be positive. And you will find the same thing. You will find that T1 minus T2 is just I divided by R alpha. But now alpha will be A divided by R, because this alpha should be positive. So it depends how you take it. Okay. So, okay. So I took 2 extra minutes. Let me stop here.
No problem, teacher.
Thank you, Hussein. Yes, so let's stop here. I wanted to solve this problem, so solve it by yourself. The solution is given. Just be careful with sometimes alpha is A divided by R. Sometimes alpha is minus A divided by R. Okay. It depends really on, it's not a big deal, but at the end of the day, you will find a minus I. You know that I is always positive, so you know that you made a mistake somewhere. Just be very careful with that. You have to be careful. Am I talking about the algebraic value, or am I talking about the absolute value? Okay. So solve this problem. I wanted to solve this problem. Unfortunately, I don't have time. The solution is given. I want to solve this problem. I want to solve this problem. These 3 problems, if I solve them, I am happy, but I'm very unhappy because I could not solve. Anyway, it's fine. We are always happy. So let's stop here. Did I take attendance?
Unfortunately, no.
Unfortunately, no. Okay, no problem. Do you want me to take attendance? Unfortunately, no. Or unfortunately,
yes.
Okay.
Yes.
So let me open the form quickly. So I really appreciate your patience. You deserve some bonus point, to be honest. What do you think, Hussein? Is it a good idea?
Yeah, we won't tell anyone.
Okay, so please check the attendance link. It's opened. So thank you very much. Let's stop here, and inshallah, see you tomorrow. We will start a new chapter. So Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala Rasulillah. So I'm recording this session, and you can watch it whenever you can, and it will be important for the next quiz, basically quiz on chapter 10, okay? The quiz next week. So I will be solving a couple of problems that are different from the previous section. So when I will record, I will upload everything, you will have different type of problems. So I think that's more beneficial for everyone if I solve different problems for different sections. And I upload everything so you can have access to the whole totality of the data. Okay, so as I said, we will solve chapter 10 recitation problems. So the first problem, I already posted this problem on Blackboard. So please have a look at it. It's already posted. The solution is given. This is in the slide of Al-Jalal. Okay. And this is an A+ problem. So this is also an A+ problem. I solved it in detail and I posted it on Blackboard. Have a look at it. Okay. I solved this problem as well. And this problem as well. It's the same type of problem, by the way. Okay. So check the videos that I posted on Blackboard already. And it's the same type of problem as this problem. And I already solved it as well, and I posted it on Blackboard. So have a look on the video that I have posted on Blackboard. Now, let's start our recitation problem for today. So let me remind you about a few things. The first is moment of inertia of different geometries. So let me use my pen here. Okay. So what is a moment of inertia of a solid cylinder or a disk if the axis of rotation is passing through the center of mass here and passing through the central axis? It's 1/2 of mr squared. Okay. Now, if I put my axis of rotation, instead of putting it through the center of mass, I put it here at the edge of my disk. Okay. This is my new axis of rotation. Let me call it axis number 2. So what is the moment of inertia of the solid disk about this new axis of rotation, which is axis number 2? I will have to use parallel axis theorem. It will be the moment of inertia around the axis which is passing through the center of mass plus mh squared, h being the perpendicular distance between these two axes. And here h is equal to r. So in other words, here it will be 1/2 mr squared plus mr squared. So I2 will become what? 3/2 of mr squared, just by parallel axis theorem. And my cylinder or my solid cylinder or my disk is rotating around this new axis of rotation. Now a rod, if my axis of rotation is a uniform rod, the center of mass is right in the middle here, and my axis of rotation is passing through the center of mass perpendicularly to the rod. The moment of inertia is 1/12 of ml squared. Now, if I shift my axis from here to the edge here to the end of the rod, so this is my new axis, I will apply parallel axis theorem. So the new moment of inertia is the old moment of inertia around the center of mass, 1/12 of ml squared plus mh squared. But here h is equal to what? L divided by 2. So I will have L divided by 2 squared. So if I do the calculation, I will find 1/3 of ml squared. Okay. When the axis of rotation is passing through the edge of the rod, the new moment of inertia is 1/12 of ml squared. When it's passing through the middle, where the center of mass is 1/12 of ml squared. Okay. When it's passing through the end of the rod, one extremity of the rod is 1/3 of ml squared. Now, a solid sphere, as we said in class, it's solid. Okay, so the mass is uniformly distributed from the center to the maximum radius r. The center of mass, the moment of inertia is 0.5, which is, 2/5, which is 0.4 mr squared. If now I have a thin spherical shell or a hollow sphere, now the whole mass is focused at the external radius. It's empty inside. So the moment of inertia is 2/3 of mr squared, basically 0.667 mr squared. And you see it's bigger than here. They have the same mass, same radius, but the distribution of my mass around the axis of rotation is different. Now, the question that I will ask you is, what is the moment of inertia of this object here if I shift the axis of rotation here? Okay. Of course, you apply parallel axis theorem. Or if I shift the axis of rotation here. Of course, you will apply parallel axis theorem. Okay, and H will be equal to R. Good. Now, let me come back to the rod. Now, what is the moment of inertia of my rod? The rod has a mass M and a length L. Now, the axis of rotation, instead of passing through the center of mass being perpendicular or being at the edge, I take the center of mass along the rod. I take the axis of rotation along the rod. So what is the moment of inertia of this rod if the axis of rotation is passing along the rod this way, longitudinally? What do you think? So what is the moment of inertia? Anyone? Okay, so it will be 0. Why it's 0? Because a rod by definition is one-dimensional, right? So as I said, in a rod, the diameter is very small compared to the length. So practically a rod is a one-dimensional object. So now I take my axis of rotation and I put it right along the rod. So you remember that moment of inertia is an integral of r squared dm. Now by putting the axis of rotation along the rod, I am putting r is equal to 0. Okay. So I took the whole mass and I put it at r equal to 0, exactly at the axis of rotation. So the moment of inertia is 0. Okay. If I have a rod and the axis of rotation is passing along the rod, the moment of inertia is 0. Does it make sense? Hello?
It makes sense, yes.
Yes, it makes sense. And this is very important in the problems that I will be giving you now. Okay. Now, let me just remind that if I have discrete particles, the moment of inertia is just sum of mi's ri square. Again, you have to remember what is this ri. Let's say this is my axis of rotation. I have a particle here, I have a particle here, I have a particle here. I have to look at the perpendicular distance between each particle and my axis of rotation. So this is particle 1, this is R1. This is particle 2, this is R2. And this is particle 3, this is R3. Okay. So these are perpendicular distance between the particle and the axis of rotation. Now, if all the particles are on the axis of rotation, of course, the moment of inertia is 0 because I am taking Ri and I'm putting it exactly at 0. Okay. Now, second thing I want to remind you is about kinematic equation when I have a rotation with constant angular acceleration. So when alpha is equal to a constant, I have this set of equations that are, as important as this set of equations. Good. Okay, okay, what time is it? Wow, okay, we'll go faster. So here I remind you the same thing, but let me just give you a brief remark here between this quadrant and this part here, okay? Or this part and this part. So I have a hoop. Okay? The hoop is a ring, okay? Like a basketball rim. Okay? It's a ring. It has a mass m and a radius r. The moment of inertia, if the axis of rotation is passing through the central axis like this, the moment of inertia is mr square. And this is in your formula sheet. Formula sheet. I will give you the moment of inertia of a hoop. The one I gave you is an axis passing through the central axis like this. But this one is not in your formula sheet. It's of course in the slide. This is in the slides I gave you. Basically, if I have a hoop, now the axis of rotation is passing through this diameter here. The moment of inertia is half mr square. So now my object is rotating in this direction, whereas here the object is rotating around the central axis. Okay. Now, if I shift the axis of rotation here, what is the new moment of inertia? You use parallel axis theorem. The new moment of inertia, I2, is the old one, half mr square plus mh square, and h is a perpendicular distance between these two axes, basically r square. And here also, if I choose an axis like this, oops, at the edge, and then my object is rotating around this axis, I can apply parallel axis theorem with respect to here. But between these two, I cannot apply parallel axis theorem because here, my diameter is my rotational axis, but here, I have the central axis here, and these two axes are perpendicular to each other. So I will not apply parallel axis theorem. I cannot go from here to here by parallel axis theorem, okay? Because these axes are perpendicular. Okay? So the only way to get it is to do the integral r squared dm, and this is a piece of cake for those of you who did Math 102 or Math 201. You will learn double or triple integral, and you will be able to integrate around a spherical, a cylinder, you know, around any shape, any simple shape, let's say. Okay, so be careful. This one is in your formula sheet. This one is not. If you need it, I will give it to you. And any formulas that you need for a moment of inertia that is not in your formula sheet, I will give it to you. Good. Now, why I'm saying this, because moment of inertia is extremely important. If I'm able to calculate moment of inertia around any axis, I'm able to apply Newton's second law for an object which is rotating. Net torque is I alpha. If I miss the moment of inertia, I will miss the moment, I will miss the torque, I will miss the alpha. Kinetic energy is half I omega squared. So I need to get the moment of inertia right. Good. Now, let's solve this first problem here. So we have a rigid structure which consists of a circular hoop. And I give you the radius of the circular hoop and a mass m, and a square made of 4 fin bars. Each of these fin bars in the square has a length r and a mass m. Now the rigid structure rotates at constant speed about the vertical axis with a period of 2.5 seconds. Assuming that r is given and m is given, calculate the moment of inertia of this structure around this axis of rotation. So the axis of rotation is the vertical here. And my object is rotating around this axis of rotation. Okay? With a constant angular speed omega. So first find the rotational inertia around this axis of rotation. Second is to find the kinetic energy, the rotational kinetic energy, which is half I omega square. Okay, so the first question is to find this I omega square. How will I get it? I gave you t, which is a period 2.5 seconds. So omega, the period is constant. So omega is constant, is 2 pi divided by t. So it will be 2 pi divided by 2.5 radian per second. And this is my omega. Once I get I just plug it here and I will get my kinetic energy. Okay, Now, first, let's find the moment of inertia of this complex structure. So my structure, my system is made of a circle plus a square. Okay, and the square has 4 parts, of course, made of 4 thin bars. Let me call this part 1, 2, 3, and 4. So the moment of inertia of my system will be equal to the moment of inertia of my circle, of my hoop, my ring, okay, my circular hoop that has a mass m and radius r, plus the moment of inertia of each bar of my square, I1, I2, I3, and I4. Now, what is the moment of inertia of my circular hoop? As I told you, when the axis is passing through the center of mass here, what is the moment of inertia of the hoop around this axis, which is passing through the diameter, according to this formula sheet? If you remember, it's 1/2 of mr squared. Okay? When the axis of rotation is passing through the diameter of my hoop, the moment of inertia is 1/2 of mr squared. Now here I shifted the axis from this to here, okay? And it's tangent, of course, and it's parallel to the old axis. So H is equal to R. So my new moment of inertia of my circle is the old one, 1/2 mr squared plus mh squared, and H is equal to R. Okay? So the moment of inertia of my circle, of my circular hoop, is just 3/2 of mr squared. Okay, so here I call it capital M, but you know, all the m's are lowercase m, small m's, okay? So you just change this by small m. So I know the moment of inertia of my circle around this axis of rotation. Now, what is the moment of inertia of fin rod number 1 around this axis of rotation? What is I1? Hussam, what do you think?
I don't really.
Yes, but what do you think? What do you think is correct? I want you to express it. So I1, part 1 of my square is this part. It's a rod. It's a fin rod, a fin bar. And the axis of rotation is passing along the rod. What is the moment of inertia? 0.
0.
Exactly. Because as I said before, I have my rod, which is just here. And the axis of rotation is passing along the rod. So I took the whole mass and I put it at r equals 0. So it will be 0. Now, what is the moment of inertia of this rod here, number 3? So this is number 1. This is number 3. This fin bar here. What is the moment of inertia of this fin bar with respect to this axis of rotation?
Multiply the distance.
I will apply parallel axis theorem. Because here, if the axis of rotation is here, it's 0. If the axis of, now if I shift it, so if the axis of rotation was here, I3 will be 0 around this axis of rotation, right? Now I have shifted the axis of rotation here. I will apply parallel axis theorem. Basically, it will be 0 plus mh squared, but the h here will be r. So mr squared. So I3 is just mr squared. Now, what is I2 and I4? What is the moment of inertia of 2? Part 2 is here, on top here. And part 4 is below here. So if I have my axis of rotation like this, part 2 of my square is here, and part 4 is here. What is the moment of inertia of part 2? So this is part 2, and this is part 4. What is the moment of inertia of part 2? Anyone? It will be equal to the moment of inertia of part 4. And it will be equal to 1/3 of mr square. Okay, because it's a rod, and we already discussed that here. So I am applying this actually. Okay. If I have a rod and the axis of rotation is at one end, perpendicular to my rod, the moment of inertia is 1/3 of ml square. And here L is equal to R. Okay. And actually I get it using parallel axis theorem. If I apply parallel axis theorem, I'll get it. So if you know this 1/3 of ml square, you will gain, let's say, 30 seconds or 10 seconds at least. And this is 1/3 of mr square. How do I get it? Because I know that if the axis of rotation was passing through the middle, it will be 1/12 of ml square, okay, plus mh square. But h is a distance between these two axes here. So the distance will be r divided by 2 square. Okay? Because here I said that the length is equal to r. This, when you do this, you will find 1/3 of mr square. Now that's it. So the moment of inertia of my system will be the one of my circle, 3/2 of mr square, plus I1, which is 0, plus I2, plus I4, basically 2 times, because they are equal, 2 times 1/3 of mr square, plus I3, which is mr square. So if you do the calculation, you get 29 divided by 6 mr square. I gave you m, I gave you r. You can calculate the numbers.
Doctor,
Yes.
I2 equal 0 or 1/3 mr square?
Which one?
I2.
No, I2 is equal to I4. I1 is equal to 0. And again, 1 is the one which is passing through the axis of rotation, along the axis of rotation. So it's 0. 3 is this one here. Okay. And that I use parallel axis theorem, because if the axis was passing through bar number 3, it will be 0. Now I have shifted the axis to a distance h, which is r. So it will give me mr square, I3. So this is I3, mr square. Now I2 and I4 are equal, okay, because both of them are rods, and the axis of rotation is just at one end of the rod. And as I told you, if I have a rod and the axis of rotation is at the end of the rod and perpendicular to the rod, the moment of inertia is 1/3 of m length of the rod square, and the length here is the radius, is r, sorry. 1/3 of mr square. So that's why I multiply it 2 times. Okay. Basically, I2 plus I4 is 2 times I2. Okay. Now, once I get the moment of inertia, the kinetic energy is simple. It's half I omega square. So I get omega here. I get I, and then I just do it. Okay. So that's what I did, and the solution is given anyway. Okay, now let's go to this problem here, which is very important. I did not have time to solve this problem with the previous section, so I will solve it now, and I will solve this one as well. If I have time, I will solve this one. Okay, I will skip this one, and I will solve this because these are very important. Okay, so let's hope that I will have more time. Is it clear what I said before, or you are focused for your Islamic midterm exam and math midterm exam?
It's because we haven't really fully studied the chapter 10, so that's why in some areas we,
Good, good.
we know
Yes,
if we studied, then we would have been able to understand fully. But we need to review this again, the recording. Inshallah.
recording. Okay, good. So I will record this and then I will post it. So whenever you study the material, take notes, okay? When you come to recitation, take notes. When you will come to it, it will be simple. Okay? Even if you will watch the recording later, take notes of important things. Okay? And then inshallah, when you will study the material, this will be simple. Okay, so let's solve this problem here. Starting from rest, a disk takes 10 revolutions to reach an angular velocity omega, constant angular acceleration. How many more revolutions are required by the disk to reach an angular velocity of 2 omega? Okay, so this is, I gave this as a quiz 2 years ago, I believe. So just let's write the data of the problem. At t equals 0, theta 0 is 0. I will take it as my reference of angular position. Omega 0 is 0 because I start from rest. Okay. And alpha is constant because I said constant angular acceleration throughout the motion. Then at t equal 1, t equal t1, theta 1 is equal to 10 revolution. Omega 1 is equal to omega because that's what I said. It takes 10 revolution to reach an angular velocity of omega. Omega 1 is equal to omega. And still alpha is constant throughout the motion. And then at t equal t2, that's the question here. I said, how many more revolutions are required by the disk to reach an angular velocity of 2 omega? So at t equal t2, the angular position will be theta 2. And I don't know it. The omega 2 will be 2 times omega because I said it. I said that it will reach an angular velocity of 2 omega. And the alpha is still constant. But here's a question. I said, how many more? So basically, I'm not interested in the absolute value of theta 2. What I'm interested is what? Theta 2 minus theta 1. Okay, this is what I'm interested in because the more has a signification here. It has a meaning. How many more revolution? Basically, from T1, how many more revolution I need to go to theta 2? So in reality, it's not theta 2 what I'm interested in. I'm interested in theta 2 minus theta 1. Okay, it's a constant angular acceleration motion, right? So alpha is constant. So I can use these 3 formulas that I gave you, like in the linear motion. So in particular, here I will just use omega final square is equal to omega initial square plus 2 times alpha theta final minus theta initial. Now I will use it between 1 and 2. So between 1 and 0 first. So I will have omega 1 square is omega 0 square plus 2 times alpha theta 1 minus theta 0. Okay. So I will have, this is omega 1 is omega. So I have omega square is 0 square plus 2 alpha theta 1 minus theta 0 is equal to 10 revolution. Okay. So that means alpha, my constant angular acceleration is omega square divided by 2 times 10 revolution. This is my constant angular acceleration. Now let me use the same formula now between T1 and T2. I will have omega 2 square is equal to omega 1 square plus 2 times alpha theta 2 minus theta 1. So omega 2, I said it is 2 omega. So omega 2 square will be 2 omega square. Omega 1 square, I know it already, is omega square. Okay. plus 2 times alpha. What is alpha? I already said it. It's omega squared divided by 2 times 10 revolution multiplied by theta 2 minus theta 1. So bottom line, I will have 4 omega squared is equal to omega squared plus this half goes away. So I will have omega squared divided by 10 revolution multiplied by delta theta, theta 2 minus theta 1. This omega goes away and I will end up with theta 2 minus theta 1 is just 3 times 10 revolution, which is 30 revolution. So my right answer is 30 revolution. Okay. So that means theta 2 minus theta 1 is 30 revolution. That means theta 2 is 30 plus theta 1, which is 10. So theta 2 is actually 40 revolution. Okay. But here I said how many more? So I want delta theta. So this is the right answer. Now let's look at this problem here. Is it clear? This should not be very difficult for you because we already did one-dimensional motion with constant acceleration. Okay. Just in physics, each word counts. Okay, no problem. So the more was the trick here. So even good students, they missed it. Okay, it happens. Now, but it should not happen frequently, let's say. Now here I have a disk, and the disk has a rotational inertia of 6 kilogram meter square. Okay, so I gave you I is 6 kilogram multiplied by meter square. Okay. And this disk has a constant angular acceleration alpha, which is 2 radian per second square. If the disk starts from rest, that means omega 0 is equal to 0. Then find the work done during the first 5 seconds by the net torque acting on it. Okay. So the question is, what is the net work? Okay. We have 2 ways to calculate the net work. Here I have constant angular acceleration. Alpha is constant is equal to 2. So I can use net torque, basically Newton's second law on my disk. Net torque is moment of inertia multiplied by alpha. Okay. So I is constant, of course, because the axis of rotation is constant, alpha is constant. So the net torque will be equal to 12 Newton meter. Okay. It will be 6 multiplied by 2, which is 12. Now the question is, what is the work of the applied torque, right? The work done by this net torque. You know that if torque is constant, the work is what? Net torque delta theta. You remember, if I have a one-dimensional force, I have work is F dot displacement. If I mean translation. Now rotation, I will replace the force by the torque of the force, and I will replace the displacement by the angular displacement. Okay. So the net work will give me 12 multiplied by delta theta. Now what is delta theta? Since alpha is constant, I know that theta minus theta initial is equal to half alpha t squared plus omega naught t. So this is delta theta. Basically delta theta will be half alpha, which is 2 multiplied by t squared, and here t is 5 seconds. So 5 squared, omega naught is 0. So I will have this 12 multiplied by half alpha multiplied by 25. Half 2, sorry, because alpha is equal to 2. Half 2 goes away, so 12 multiplied by 25, this will give you 30 joule. Okay, this is what we did yesterday. Okay, it's in your formula sheet, and this is true for a constant torque. And here I know that the net torque is constant because alpha is constant, I is constant, net torque is constant. If I don't have a constant torque, the work is just an integral of F delta theta. It's like when I don't have a constant force, the work is integral of force dx. Now I replace the force by the torque of the force. I replace dx by d theta. Okay. Now there is another way to calculate this network. So the network is 300 joules. Another way to calculate the network is work kinetic energy theorem. Network is the work of the net torque is equal to change in kinetic energy. It will be kinetic energy final minus kinetic energy initial. But you know, we are in rotation. So kinetic energy final is half moment of inertia omega final square minus half moment of inertia omega initial square. But omega initial is 0. So this is 0. So I will have half moment of inertia. It's a disk. And then I gave you the moment of inertia. It's 6. Now omega final. It's a constant acceleration motion. That means omega final is equal to omega initial plus alpha t. Omega initial is 0, so it's just alpha t. So alpha is equal to 2, t is equal to 5 square. And you do it and you will get the same answer, which is 300 joules. Always live to Makkah, okay? And you do Umrah and you pray for us, inshallah. Is it clear? Okay. Now, let me go to the next problem here. I did not have time to solve this problem, unfortunately, in the previous section as well. Now, here we have a particle which is rotating in a horizontal plane. Take notes, okay? Don't hesitate to take notes, okay? Even if you will watch it later. So, a particle is rotating in a horizontal plane about a fixed axis. The radius of the circular path is given. R is equal to 10 meters. And the particle starts to rotate at constant angular acceleration. So alpha is constant from rest. So omega 0 is 0 at t equals 0. Now here, this is what I gave you. The angular speed for the particle reached 36 revolutions per minute at t equal 8 seconds. So omega at 8 seconds is equal to, let me call it omega 8, is 36 revolution per minute. Okay. So I know that I have to put it in SI units. So it will be 36. 1 revolution is 2 pi radian. 1 minute is 60 seconds. And I get it omega 8 in radian per second. Now the question is, when the time is 5 seconds, what is the magnitude of the particle's radial acceleration? So the question is, at t equal 5 seconds, what is AR5? Okay. The radial acceleration of my particle. I will ask another question. And also, what is the tangential acceleration of my particle at t equal 5 seconds? Okay. You know that these are linear acceleration. You know that my linear acceleration has 2 components, the radial component and the tangential component. The radial component, as we said, is a centripetal acceleration, is v squared over r. So v is r omega. So I will have r omega square divided by r. So this will give me r omega square. So when I have a rotation, I will not say that the centripetal acceleration is v squared over r. I will say that the centripetal acceleration is r omega square. It's the same by the way. Okay. You just replace v by r omega, you simplify by r. So you have radial component of my acceleration is r omega square. And the tangential component of my acceleration, this is r alpha. Okay. So be careful. Sometimes I call it capital R, sometimes small r. So you get my point. Okay. It's just the radius. So since I'm using small r, let me just put here r alpha. So here, let me put r. Okay. So I need, first, let me get alpha. Alpha is constant because that's a key word here. I know that omega 8 is equal to omega 0 plus alpha t. Okay. That means alpha is omega 8, and I know omega 8 is here. I know omega 0 is 0 divided by t, which is 8 seconds. So I can get alpha easily. I just take this and I divide by 8 seconds. Now, once I get alpha, and it's constant, of course, I know that omega at any time is omega naught, which is 0 plus alpha t. Okay. So that means omega 5 is alpha multiplied by 5. So that means the radial component of my acceleration at 5 is just equal to r omega 5 square. So it will be r is equal to 10. Omega 5 will be equal to what? This, alpha multiplied by 5 square. And I know alpha. Okay? I know alpha because it's omega 8 divided by 8 seconds. Good. And then the tangential component, AT at 5, is simple. It's just r, which is 10 multiplied by alpha. And alpha is omega 8 divided by 8. Basically, this divided by 8. Okay. So this is not very difficult, but you have to be careful. Okay. This is what I did here. This is omega 8, and then this is alpha, and I get it. AR at t equal 5 is r omega square. Okay, omega 5 is what I need. How do I get omega 5? Is alpha multiplied by 5, and I get it here. So AR is just this. Okay. So in some problem, I will ask you what is the ratio between AT and AR. Okay. But you will see the recitation problem and you will solve it. I will skip this example because I solved it in the previous section, and the detailed solution will be posted. I will post both recordings. Okay, now let's go to this problem. I want to solve this problem, and I want to solve this problem here. This one I will not have time, unfortunately. Okay, let's look at this problem here. Okay, so is it clear what I'm saying, or still not very clear? Okay, when you will review, it will be clear, inshallah. Okay. When you will review the material. Okay. So
Yes, sure.
your silence, I will postpone the lab. I will postpone the quiz on chapter 10 because your silence is worrying me, actually. Okay, so I will postpone quiz number, chapter 10 quiz. I'll put it next Tuesday, not tomorrow, but the following one. And we have quiz on chapter 9, inshallah, this Thursday. You can announce it on WhatsApp group after the class. Okay. Now here, I will not solve this problem directly, okay? Because, you know, it's, you will see. Let me solve it analytically. So here I give you a block M1 and a block M2. So M1 is 0.46 kilogram and M2 is half kilogram. So M2 is bigger than M1. So what do I know? Of course, if they are attached for the system, M1 will go up and M2 will fall down. Okay. So this is the acceleration here. This acceleration will be down. Now, before I used to say something very important. I used to say that the pulley is massless. Now the pulley is not massless. The pulley has a mass and it has a radius. So the pulley has a moment of inertia. So the pulley has a moment of inertia. And by the way, that's the last question. What is the rotational inertia of the pulley? Okay. So the pulley is participating in the rotation. So if in this type of problem, I will have to apply Newton's second law on each block, and also I have to apply the Newton's second law on the pulley, because now the pulley is rotating and it has a moment of inertia. So let's assume that the question is find the acceleration of the system, the linear acceleration of the system. Okay. What is the linear acceleration of the system? This is a question that I'm asking you. I'm not following this. Okay, I will come back to this. In this problem here, in specifically, the linear acceleration can be, I can get it from the first, this line here. Okay. And then I start getting the rest. But my question is more general. I have two blocks of mass M1 and M2, and they are attached using a cord, which is unstretchable, massless, unstretchable, and using a pulley. Now the pulley is not massless. The pulley has a mass and a radius, so it has a moment of inertia. So the first question that I'm asking you is, what is the linear acceleration of this block? This block is moving up, this block is moving down. Of course, the magnitude of the acceleration will be the same. What is that magnitude of acceleration? That's number one. Number two, I will ask, what is the angular acceleration of the pulley? Because now the pulley is rotating. Okay. And number three, I will ask, what is the tension T1 and what is the tension T2? Which one will be bigger between the tension here and the tension here? What do you think? Which tension should be bigger here?
I think, Dr. Tension 2.
Exactly. Because here, since this is moving up, this is moving down, my pulley is rotating in the clockwise direction. Okay. So since it's rotating in this direction, that means the tension in that direction is dominant. If the tension here was dominant in the T1 was dominant, the pulley will be rotating in the counterclockwise direction. But tension 2 is bigger because tension 2, my pulley is rotating along the direction of the dominant torque. Okay? And we will come back to that. Now the tension 1 and tension 2 are not equal because now moment of inertia is not zero. The pulley is not massless. Okay, now that's the problem. First, let's start to get acceleration, then we get the tension, then we get the angular acceleration, then etc., etc. Okay, so as I said, I have to apply Newton's second law on this block, M1. Of course, here I will have M1G, here I will have T1. Okay, here I will have M2G, and here I will have T2. So if I apply Newton's second law on block 1, I will have plus T1 minus M1G is equal to plus M1A. So this gives me T1. T1 is just M1G plus M1A. If I know A, I will get T. Of course, A is positive here. A is the magnitude of the acceleration. Now let me apply Newton's second law on M2. So on M2, I will have T2 minus M2G is equal to minus M2A because the acceleration is downward. That's why I put the minus here. So that means this A is positive. Okay. The minus is already put here. So that means T2 will be equal to M2G minus M2A. Okay. So that means if I know A, I will know the tension. 1 and 2. Now I will apply Newton's second law on my pulley. So on the perspective of the pulley, tension 2 is downward here. And tension 1 is also downward. Okay. But tension 2 will make my object rotate negatively, but tension 1 has a tendency to make my object rotate positively. Okay. So if I apply Newton's second law on the pulley, I will have net torque is I alpha. So of course the pulley has a weight, gravitational force, but it also have a normal force from the support of the pulley. But these two forces have net torque equal to 0 because they are radial forces. They are passing through the center of mass, so the momentum is 0. So torque of gravitational force is 0, which is equal to torque to the normal force. So the only forces that have real torque, meaning that induce an acceleration, is T1 and T2. Okay. Now, let's do it this way. So this net torque will be torque of T1 plus torque of T2 is equal to I alpha. Normally, let me say this. Normally, alpha is negative. Why? Because this is rotating clockwise in the negative direction. So alpha should be negative. Okay. But what I will do, I will take the absolute value of alpha. Okay. So of course, absolute value of alpha is positive. But in reality, physically, I know that rotating in the negative direction, alpha is negative. Okay, let's keep it this way. Let's say alpha is negative. So what is torque of T1? T1 is here, okay, and it's down here. And here you have 90 degrees. So it will make my object rotate in the positive direction. So the torque of T1 is plus T1R, because sine 90 is equal to 1. What is the torque of T2 here? Here also it's 90 degrees. It will be minus T2R. And this is equal to I alpha. But here, of course, alpha is negative, okay, because I know that it should rotate. So basically, I'm telling you that minus T2R is dominating T1R. Okay, that's why alpha is negative here. So in other words, I will have what? Let me just have T1 minus T2 is equal to I divided by R multiplied by alpha. So I just divided by R, okay? And you see, this is what we used to have. Before, we used to say that the pulley is massless. If the pulley is massless, I is equal to 0, and I say that T1 is equal to T2. If the pulley is massless, the moment of inertia is 0, and you see that the tension here is equal to the tension here. But now the pulley is not massless anymore. So that means that T1 minus T2 is equal to I divided by R alpha. Okay. Now here I have to say something very important. The linear acceleration of the block in magnitude has the same magnitude as the tangential acceleration of the pulley. And the tangential acceleration of the pulley is R alpha. And of course, I'm taking absolute value. So here, alpha. So absolute value of alpha is just the linear acceleration of the block divided by the radius. And this is happening because there is no slipping. Okay. So they have to be connected. The linear acceleration of the block is equal to the tangential acceleration of my pulley in absolute value. So absolute value of alpha is A divided by R. That means that the real value of alpha is minus A divided by R, because A is positive, okay? But alpha is negative. So alpha is minus A divided by R in this configuration. So I will have T1 minus T2 is equal to I divided by R, and I replace alpha by minus A divided by R. So bottom line, I will have T2 minus T1 is just I divided by R square A. Okay. So what time is it? Subhanallah al-Azim. It's time. Okay, you were very patient, guys. So Jazakumullah khairan. Let's stop here. And I will remember this, of course, because you were patient. So I will postpone the quiz on chapter 10, and probably I will give you extra minutes, inshallah. Because, you know, if you do good, you deserve something good. And I believe that you are doing good. Okay, so let me stop here. I will take attendance, so mark yourself present, and inshallah, see you tomorrow. Next time, when it's time, let me know, okay? Because I was too focused, so let me know. And so let me just write this. This is the final answer. And then, so as you are writing, you are marking yourself present. At the end of the day, I will find A is equal to M2 minus M1 divided by total mass M1 plus M2 plus moment of inertia divided by R square multiplied by G. So this is the final answer. Now, once I get A, T1 is easy. As we said, T1 was just what? M1G plus M1A. So I just take A and I plug it here. And then T2 as well is easy. T2 will be what? M2G minus M2A. And you plug it here, you get A, you plug it here, and you will get. Here's something I have to say, which is very important, is always, as I think Sufyan said, T2 is bigger than T1, okay? Because the dominant torque, I am rotating in the direction of the dominant torque. So the dominant torque is driven by T2, okay? And T1 is smaller than T2. I had time to solve this problem in the previous section, so you will check the solution. Thank you very much, and inshallah, see you tomorrow. Assalamu alaikum.
Thank you, Doctor.
Thank you, Doctor.
Patience.
Thank you.